do now is kind of take you guys back a little bit to Chapter 2 to build up a first law analysis. So in Chapter 2, we went ahead and introduced the concept of energy and energy transfer. But in this chapter, what we're going to do is bring all of that together into a complete first law analysis for closed systems. But before we actually get into that, what I want to do is just give you an example of what first law analyses are for. Sometimes we end up getting into explaining things about a certain concept, but not really understanding why we're doing it, what it's for. Let's take the example of a piston cylinder assembly. Right, I have a piston cylinder assembly here where the piston is free to move against the atmosphere. So any sort of process energy transfer by heat to the system will result in a constant pressure expansion where the piston acts against the atmosphere. Right, so in a typical first law analysis, we would start out by writing the first law in its most compact form. Right, this means all energy in by heat, mass, and work minus all energy out by heat, mass, and work equals the total change in energy of the system. So if you look at this problem statement, this first step you'd be writing this out. The second step would be going ahead and putting in the energy terms. So what do we have going in? Well, we have Q going in, right? Energy in by heat, mass, and work. There's no work going to the system, and there's no heat crossing the boundary. There's only heat crossing the boundary. Minus the fact that there's boundary work going out equals the change in energy of the system. The change in energy of the system is the total of the internal energy and the kinetic energy and the change in potential energy. In this case, for a stationary system, it's delta U. Next step would be to evaluate the process, some of the process functions here, right? So, or path functions. For example, in this case, boundary work, right? In its fundamental form is the integral of the pressure over the volume. And in this case, it being a constant pressure process, we would get pressure, the work being the pressure times the change in volume. So if I wanted to use this to solve for Q, I would get Q in is equal to delta U plus P delta V, right? This is in this special case of a constant pressure process. I could also expand this a little bit, taking into account enthalpy, simplify this. If you remember, enthalpy is internal energy plus pressure times volume. Now, in this case, I have a state 1, so the internal energy, or the enthalpy of state 1 is equal to the internal energy state 1 plus the pressure of state 1 times the volume state 1. And at state 2, I have the enthalpy at state 2 equals the internal energy at state 2 plus the pressure at state 2 times the volume at state 2. Now in this case, this is a constant pressure process, so the pressure at state 1 is equal to the pressure at state 2. So if we evaluate if we go ahead, we can actually substitute in for delta U plus P delta V as delta H. If you look at this algebraically, we get the H2 minus H1 is equal to U2 plus, since the pressure is equal to state 1 to state 2, we just replace that with pressure. So U2 plus pressure times volume at state 1 minus U1 plus pressure times volume at state 1. But pressure at state 1 is equal to pressure at state 2. So we end up with delta H is equal to U2 minus U1 plus pressure times V2 minus V1. Right? So basically this is telling me that delta U plus P delta V equals delta H. Now, this is for the special case of a constant pressure process, right? What I have is a piston pushing up against the atmosphere, and what I'm doing is I'm trying to compute the total heat flow to the system that causes the piston to move up a certain distance. Let's say I'm looking at the piston moving up a certain distance x, right? And I want you to tell me how much heat is required to the system for that piston to move up a certain distance x. I would evaluate this problem. I would do a first law analysis. I realize that for a constant pressure process, I have boundary work is P delta V, and this problem would simplify that the Q in is equal to delta H. But what if I had something acting against the piston, right? What if I had a spring, right? Now, as this piston moves up, it's pushing against the spring, causing the spring to compress, requiring more boundary work, right? So now, this whole concept of this being P delta V goes away, right? Because it's not a constant pressure boundary work. So my work is left in integral form, where now I have to evaluate my pressure, integrate the function of pressure over the volume. And this does not no longer equals delta H because now my boundary work is not constant pressure. So it actually requires more Q, more heat in order to be able to push the piston against the spring. Basically what I'm getting at is that this whole first law analysis allows me to analyze that. It takes what is state dependent. So on the right hand side here, this part of the equation, delta E, is a state dependent quantity. Right, delta E of the system, the change in energy of the system just has to do what happened, right? The system went from one state to another, and the change in energy is just this energy at one state minus the energy of the other state. Regardless of how the process happened, the change in state is just a change in state. But these variables, E in and E out, they are both path-dependent functions. Those values, those quantities depend on how the process occurred, or what, in this case, we had constant pressure process, right? That we analyzed it, where the boundary work is P delta V. But if my pressure is not constant, right, and I actually have a functional pressure change over a volume, then what happens is that I have to integrate that pressure over the volume in order to get the boundary work for the fact that I have the piston pushing against the spring. And that changes the path-dependent quantity of the heat. It changes the value of the heat. It means I have to actually add more heat to the system to make that happen. Let's try another example. Let's say I have a rigid tank, right? In this case, the rigid tank means that the volume of the tank is constant. How do I evaluate first law analysis if I wanted to look at quantifying the amount of heat added to a tank, right? I have heat into a tank. What if I want to analyze that? How do I do that, right? Well, again, same steps in the first law. I write out my first law in its most compact form, right? E in minus E out equals delta E system. Then I go ahead and quantify each of the terms, or try to specify each of the terms. E in, do I have any energy crossing the boundary in the form of heat, mass, and work? Yes, I have energy going in the form of heat. Do I have any energy leaving in the form of heat, mass, and work? No, nothing. Do I have any change in energy of the system, being the change in internal energy, the change in kinetic energy, and the change in potential energy? The system is stationary, so PE and KE changes are zero, and I'm left with just the change in internal energy. So in this case, I have Q in equals delta U. Again, same analysis, same steps required, or same steps of analyzing the problem are carried out, and it gets the first law into a final form that's appropriate for this problem. So this is eventually where we're going. We're being able to take path-dependent quantities and relate it to state-dependent quantities based on how the process occurred. So that's where we're going with this chapter. So let's back up a little bit and let's start from the beginning. What is the first law, right? Again, some of this is repeat from chapter 2, but I believe it's worth going through in order to bring everything together. So the first law, it provides a basis for studying relationships among various forms of energy and energy interactions. The concept is that energy can neither be created nor destroyed, it can only change form. So consequence of the first law is the definition of the property of total energy. Another way to word first law is an energy balance, and it basically means you're looking at the net change of total energy by energy entering by mass and leaving by mass, energy entering by work, leaving by work, entering by work, and energy entering by heat and leaving by heat, right? It is the net change in the total energy of the system during a process is equal to the difference between the total energy leaving and the total energy entering. And energy can only leave and enter in the form of heat, mass, and work. So an energy balance is exactly what we were just doing earlier. It is equating the sum total of energy in minus the sum total of energy out and equating that to the total change in energy of the system. And this relationship is valid for any system undergoing any process. So what I'm going to do now is go ahead and break up each part of the first law. So let's go ahead, let's take delta E system, right? Let's take that from this slide and let's slap it on this one. So what we're going to do right now is define what delta E system is, independent of E in and E out. I just want to define and how to quantify delta E system. Delta E system is simply the change, the energy change of the system, right? It's the total energy between the final and initial state. Basically, what this equates to is that the total change in energy of the system in the context of this first thermodynamics course is equal to the sum total change, the total energy plus the change in the kinetic energy plus the change in potential energy. So again, delta U is just equated to be, for a closed system, right? This is a special case of a closed system where mass is constant. My change in energy of the system, internal energy of the system is equal to mass times the change in specific energy of the system. Then I have delta KE, which is equal to 1/2 times the mass times the final velocity of the system squared minus the initial velocity of the system squared. And then the change in potential energy, the change in potential energy would just be mass times gravity times the change, change in height of the system. Now, in the special case of a stationary system, right, stationary system that's not moving, that means that the change in kinetic and potential energy of the system is 0. Let me define real quick what I mean by change in kinetic and potential energy. What I mean is the system itself. Right? In the prior example problem, we had a piston cylinder device. And I have some people that would say, like, well, if the piston is moving, that means there's a change in potential energy of the system. And that's not correct because the piston is part of the system. It is not the whole system. The whole system is the piston cylinder assembly, and the piston cylinder assembly as a whole is not moving. It's just one boundary that's moving. So in the case of a piston cylinder assembly, it's stationary. So the system's not moving. I mean, the piston cylinder assembly, the assembly itself does not have a velocity. It is not moving. And it doesn't change height. So the change in kinetic potential energy would be 0, basically equating that for a stationary system, the total change in energy would be the change in internal energy. Now, let's go back and let's now take E in minus E out. And let's slap it over on this slide. And we'll go ahead and quantify E in minus E out. E in minus E out is basically just the difference between the heat in minus the heat out, energy in and energy out by mass or by heat, plus the sum of energy in and energy out by work, plus the difference between the sum total of the energy in by mass minus the energy out by mass. So we take this whole thing, and the compact form again comes back to E in minus E out equals delta E system. Now, there's different ways to write the first law. It can be written in rate form, right? Rate form meaning that there is energy entering and energy leaving the system at a specified rate. It can be written in per mass form. And everyone's favorite, it can also be written in differential form. Now, I want to specify that in this case of closed systems, right? Again, just to repeat, this chapter focuses on closed systems. Closed systems mean that mass does not cross the boundary. Chapter 5 will be looking at open systems where mass does cross the boundary. So if we go ahead and we have this special case, now be careful because some people see these things and they're like, oh, well, if I take this equation from this slide, that means for all times, always, this equation applies for first law analyses. But you forget that this is an energy balance for a closed system. In the case of a closed system, in the case for an open system, you have to include mass terms. So in this case, we have En minus E out equals the sum of the energy in minus energy out by heat plus the sum of the work, the energy in and energy out by work. And in the case delta E system equals delta U plus delta KE plus delta PE. Okay, and if we were to go ahead and just take a look at it, you can actually see that there's another notation that the energy balance for a closed system can be equated to be, again, the heat total Q minus W equals the change in internal energy plus the change in kinetic energy plus the change in potential energy. Now, in general, there's the general total energy terms. For stationary systems, the delta E becomes just delta U, like we mentioned earlier, because delta PE and delta KE are 0. You also have it per unit mass basis in differential form.